Okay, this is a video on 13.5, okay. But before we get there, I just want to bridge us. I always like doing that. I want to take us from what we know to the new knowledge. Okay, so 13.4, we looked at the equations of motion, rectangular coordinates. Okay, so what did we say here? Well, essentially what we found is that if we have rectilinear motion, okay, most likely then, which is straight line motion, we would use the rectangular coordinate system, okay? And what does that mean? It means basically we started off with this generic equation, sum of the forces equals mass times acceleration, and we applied this general equation. Remember guys, that's the general equation. But we applied it to our rectangular coordinate system, which means that we started off with sum of the forces equals ma. But what does that mean? It means sum of the forces in the x plus sum of the forces in the y plus sum of the forces in the z, etc. equals mass times the acceleration in those three directions, right? This is just the rectangular coordinate system. That's all. And then we said, well, let's extract the x. Sum of the forces in the x should equal mass times acceleration in the x, and that's what we had there. Sum of the forces in the y should equal mass times acceleration in the y, etc., etc. Okay? So the point is, we took our general equation of motion, and we applied it to rectangular coordinates. And in general, when we have rectilinear straight line motion, we use rectangular coordinates, okay? In the same way, now we come to chapter 13.5, and what I said in the previous video is that if we've got curvilinear motion, in general, we are going to use normal and tangential coordinates, okay? So have you got that? 13.4, rectangular coordinates are used in general for rectilinear motion. And 13.5, normal and tangential coordinates are used for curvilinear motion. In general, okay? I'm just saying in general, that's what this textbook uses. All right. Now, what do I want to say here? Again, we take the general expression for the equation of motion. Sum of the forces equals mass times acceleration. That's the general expression. This general expression doesn't tell us what coordinate system it's in. So now we've got a curvilinear motion, and we want to use the normal and tangential coordinate system. So we need to then essentially convert this into normal and tangential coordinates. But now, what we were used to, just come down here quickly, in chapter 12:7, we only discussed the normal and tangential coordinates. So again, say now we had some curved motion, and we said there's my normal, there's my tangential, for example. Okay? I think I drew that incorrectly. That should be there. Okay? But what we didn't take into account here was the third axis. Okay? So recall with the rectangular coordinate system, you've got the XYZ axes, right? Well, what's the third axis here? The third axis is the binormal direction. Okay, I know this is a shocking drawing, but okay, here's a better one. Here you have curved motion of a particle. There's the particle at that point. The normal direction is to the center of curvature. The tangential direction, we know this, there's nothing new here. But we'd like to introduce this third direction, which is the binormal direction. And these are all perpendicular to each other, okay? So it's exactly like a XYZ axis. They are three perpendicular directions, all right? So we're used to the normal and the tangential, but now we'd like to introduce the binormal direction. And essentially, you please take note of this. Note that there is no motion of the particle in, okay, that's an in, by the way, in the binormal direction. There is no motion of the particle in the binormal direction since the particle is constrained to move along the path. Okay? So what are we saying? As this moves along the path, it's important that we define this direction because it helps us, when we calculate our forces, it helps us calculate important information. But our assumption is that there's no motion in this binormal direction. Okay? So what does that mean? Okay, so we take our equation of motion and we apply it to the normal, tangential, and binormal directions. This is what we should get here. The sum of the forces in the tangential plus forces in the normal plus the forces in the binormal should equal the mass times acceleration in the tangential plus mass times acceleration in the normal plus mass times acceleration in the binormal. But the acceleration in the binormal is 0. So that's why they didn't include it there. I don't know why they didn't. They should have included it there, but they didn't. Okay, and then if you say, okay, let's take the tangential components, sum of the forces in the tangential direction should equal mass times acceleration in the tangential. There we go. Normal, normal, okay? And then binormal is 0, so take note of that, okay? So I think that's all that I want to say for this. Hope that helps. Cheers.